In the previous video, I was talking about using AMR, abstract meaning representation, for event extraction, but today I'm gonna be focusing on just biomedical scope, in the scope of biomedical text. So this paper in 2017. We propose a novel abstract meaning representation-based approach to identify molecular events or interactions in biomedical text. So our key contributions are an empirical validation of our hypothesis that an event is a subgraph of the AMR graph, a neural network-based model that identifies such an event subgraph given an AMR. A distance supervision-based approach to gather additional training data. Of course, distance supervision, there are many forms of that, but most of them are very noisy, induce noise, so we should always implement noise cancellation as well, because we don't know those labels are good or they are false. This is an AMR with simple event annotation. You see that this one you can consider this as a subgraph. So the subgraph rooted, for example, at phosphorylate 0,1 identifies the event E1, and the subgraph rooted at induce 0,1 identifies an event E2. We hypothesize that an event structure is a subgraph of DAG structure like AMR, and so this is directed acyclic graph. Our first contribution is the testing of the above hypothesis that an event structure is a subgraph an AMR graph. Given a sentence, we automatically obtain its AMR using an AMR parser and explain how an event can be defined as a subgraph of the AMR graph. So this is Genia 2013. You see some of these triggers have only protein as their argument, protein, but some of them are nested because they are not only have protein as their, an entity as their argument, but also an event. So that's why we call these nested events. So this is an example of event annotation. The protein annotation are given as starting point. So these are triggers and events. So the second contribution is a supervised neural network that is trained to identify an event subgraph given an AMR. Our model is built, so it's a good, consider AMR as a good feature and representation. Our third contribution is distance supervision that I said based on this approach to collect additional annotated training data. Distance supervision works on the assumption that given a known relation between two entities, a sentence containing the two entities is likely to express this relation and hence can serve as training data for that relation. So the task description is that the model description is that we identify protein nodes and interaction nodes in the graph. Protein node identification we use in both training and test set. Protein terms are pre-annotated. We then use this AMR graph alignment information to identify nodes in the AMR graph aligned to these protein terms to get our protein nodes. In the training data, interaction terms are pre-annotated. To identify interaction terms in the test set, we use the following heuristic. Any term that was annotated as an interaction term more than once in the training data is considered as an interaction term in the test data as well. We then use the AMR graph alignment information to identify nodes in the AMR graph aligned to the interaction terms to get our interaction nodes T. So given P and T, we identify an event subgraph using the following two subprocesses. First, theme identification, because for every P sub I, and T sub j, so where P sub I is in P and T sub j is in T is a candidate for an event E sub m, because the type is Tj and the theme is P sub I. Type is one of the 9 event types in table 1 that I showed you. If E sub m can take other events as arguments, and if shortest path between T sub j and P sub I includes an interaction term such that the pair is an event, then we define the event E sub m, and we usually write this. For cause identification, for events E sub m that can take a cause argument, we identify possible candidates for their cause by again looking at for all pairs where P sub L is in P and add cause to the event. Since these events can even take other events as their cause argument, we identify additional candidates for their cause. So upper bound using event is a subgraph AMR hypothesis. Before we learn to identify event subgraphs from the AMR graph, we first calculate the upper bound that we are setting for our model, because we are using an AMR parser instead of obtaining gold AMRs. For calculating this upper bound, we first obtain the AMR graph of a sequence using the AMR parser, and then assume that if an event is a subgraph of this AMR graph, then we can identify it correctly. By using this hypothesis, we have set an upper bound of 74% F1 score. As the accuracy of automatic AMR parsers improve, our model will perform better on event extraction. So you see the theme identification and cause identification stages. And they use LSTM-based learning model. But for initialization, we have two choices. We can initialize the embedding in the input layer randomly, or we can initialize them with values that reflect the meanings of the word types. But during test time, we first make predictions using our LSTM model for theme prediction. For every pair with a non-zero label, we construct events as false. For label L corresponding to interaction types that take only proteins as theme arguments, we construct events as E sub m. For label L corresponding to interaction types that can take another event as its theme, we look at the path between the T sub j and P sub I in the AMR. If this path includes a pair that has a non-zero label, then we construct an event where E sub P is the event constructed from the pair. Otherwise, we construct an event type and theme. Distance supervision, as I said, is as a learning paradigm was introduced in 2009 for relation extraction in general domain. They use freebase to get a set of relation instances and entity pairs participating in those relations. extract all sentences containing those two entity pairs from Wikipedia text and use these sentences as their training data. This work and many others show that distance supervision yields significant improvement in relation extraction. Neural network models like LSTM need to be trained on substantial amounts of training data for them to be able to generalize well. However, due to lack of labeled data in biomedical domain, most work in relation extraction in this domain has been restricted to purely supervised techniques. So in this work, we cope with this problem by gathering additional training data using distance supervision from a knowledge base. It's very automatic. Once you know the relation, then you can just project on your text and see, oh, these are annotated successfully and automatically. More data, better deep learning. AMR pass-based selection. The traditional distance supervision approach says that all the sentences extracted using the method above can be used as additional training data, under the assumption that all sentences in which the protein co-occur express the relation mentioned in the database. However, this article notes that this approach can often lead to a lot of false positives. As I said, it's very noisy, this distance supervision. So this article have discussed several prior work that try to reduce such noise. In our work, we develop a novel selection technique for reducing such noise using AMR pass heuristic. We make the observation that given two protein nodes in an AMR, if there is a relation between the two, then the shortest path between the two protein nodes in the AMR contains the interaction term expressing the relation R. So you see here, and there's no interaction term corresponding to relation exists. These are mapping between event types and BioPAX model relations. For any relation, we have an event type. And we use BioNLP 2011, 2013, 2009. And they train it on both abstract and full text collection. And the rest of them is about a phone score which is still low, 50%. Even if you use distance supervision, it's very low. And if you use LSTM, is 46, so it's a very small improvement. We can ignore the improvement. So distance supervision is not playing a role here.